Okay, so now we are recording. We are very happy to have Luciano Pomatto from Caltech talking about monotone additive statistics. So you have 1 hour. The floor is yours, Luciano.
Thank you, Antonio, and thank you a lot for inviting me. Had a nice time today, and thank you for being here. So I'm excited to tell you about this paper. This is a joint work with Xiaosheng Mu, Philip Storak, and Omer Tammuz. And together we've been thinking for a while about some basic issues on stochastic orders and how to summarize distributions. So let me jump in and tell you what I want to tell you about today. So the basic idea is as follows. So like in economics, like in many other fields, we routinely work with probability distributions. And a classic questions that we encounter all the time is how can we summarize some aspects of a probability distributions using a single number? The way we do it, right, in statistics, in economics, operations research, in finance, etc., is through some descriptive statistic. Say the expectation, the median, the variance, maybe the certainty equivalent computed with respect to some utility function U over money, or some more sophisticated risk measure, like value at risk, etc., if you're familiar with that sort of ideas. So this paper is divided into two parts. This project is divided into two parts. In the first part, I will discuss some material that one of my co-authors calls abstract nonsense. So this is going to be some sort of a new characterization of a new family of descriptive statistics that satisfies some very basic properties. And this is going to be somewhat removed from any specific context and application. And then in the second part, I will try to convince you that some of this characterization that we provide, this new class of descriptive statistics that we find, actually can be useful in thinking about a couple of problems in a single agent decision-making, but also in multi-agent decision-making. So let me jump in and tell you first what is this abstract result that we find and what sort of ideas it can capture. So I will think of a descriptive statistic, or just for lack of a simpler word, just a statistic, just as a map from random variables to real numbers. And this statistic will satisfy two main properties. The most important property is that if two random variables, have the same distributions, then they must be assigned the same number. So think about this phi of x as a summary of some property that the distribution of x possesses. And the other property we're going to look at is a sort of normalization property. I call it a normalization because with the other properties I'm going to describe, this really amounts to a simple normalization by a constant, which says that the statistics, when evaluated at a constant random variable, is equal to the constant itself. Think about the expectation of a constant or the median of a constant random variable. So we're going to work with statistics that satisfy two properties. The first one is monotonicity in first-order stochastic dominance. Okay. This is a well-known idea, right? We have two random variables x and y. They are ranking first-order stochastic dominance if the expectation of x is greater than the expectation of y with respect to any strictly increasing transformation u. If x and y are seen as lotteries or assets, right? This says that any decision maker with expected utility preferences and increasing utility over money will prefer x to y. Typically, we think about this ranking in terms of some characterizations, such as the point-wise ordering of the CDFs, or in terms of a coupling. So x dominates y in first-order stochastic dominance if and only if you can find the other two random variables, x prime and y prime, with the same marginals, the same original distributions, but where x prime dominates y prime point-wise, is greater point-wise. So I'm going to call a statistic monotone if it is increasing in this stochastic order. If whenever x is greater than y in first order dominance, then phi of x is greater than phi of y. So of course, the expectation satisfies this, is monotone in this sense, but many other statistics. Think about the median or any other quantile or combination of quantile will satisfy this property. This is really a basic condition.
Sorry, one quick clarification. Are X and Y on these slides the statistics or the random variables?
The random variables.
Okay.
The statistic is going to be phi.
Phi, okay.
Right, capital phi, some mapping from random variables to numbers. Okay, so monotonicity is somewhat a routine property in many contexts. So here we come to our main property of interest, which is a form of additivity. So I'm going to call a statistic additive if it satisfies the following. If phi evaluated at the sum of independent random variables is equal to the sum of the individual values, right? So phi of x plus y is equal to phi of x plus phi of y, whenever x and y are stochastically independent random variables. Okay. So let me tell you right away what is going to be the key question I'm going to talk about for the next half hour or so is understanding what are the statistics that are monotone and additive. Okay, so why do we care about additivity? Okay, I don't have a one-line answer to this, but let me tell you how we got here. So first, of course, there is the intellectual curiosity. So if you think about any statistic, median, expectation, variance, and so forth, the way we usually teach them, the students, is in terms of their properties, right? The expectation is a linear functional of the random variable. The variance is additive for independent random variables. So there is something about understanding how statistics behave with respect to aggregation of different sources of randomness that seems fundamental. And when we started to think about this problem, we quickly convinced ourselves that this question of characterizing additive statistics must have been solved in the 50s or the 60s or maybe the 70s, but then we actually found out that there is very, very little work on this and no actual characterization in the literature. Okay, maybe closer to economic theory, I will show you some context where actually this additivity property can be natural. And in fact, it is related to some ideas that are already quite well known in economic theory, such as the idea of stationarity for time preferences. Later on, you will see what I really mean by this. Let me just give you a little appetizer of where I'm going with this property in its connection with economic theory. Imagine, let me give you two pedestrian examples. Example one is that of a driver who has to go from A to B and has to choose between two possible roads, X and Y. Now, X and Y are random variables. They don't represent money, but rather they describe the time that it's going to take the decision maker to go from one point to the next on that road. And our decision maker will associate to any possible random time a number, phi of x, and then choose the lower one. So think of the phi as some kind of index, some kind of representation of the decision maker preferences over this random time. Now, monotonicity is natural, actually anti-monotonicity. I prefer a road where the distribution is stochastically smaller, the distribution of waiting times. But what about additivity? Here, additivity basically says the following. Imagine that after going from A to B, I also need to go to C. And from B to C, there's going to be an additional waiting time that is stochastically independent from X or Y. And here, additivity captures this idea that in my choice between X and Y, because the random time that comes from Z is independent, that should not affect my choice. So imagine that your index phi satisfies the following property. If phi of X is greater than phi of Y, if I prefer X over Y, then I prefer X plus Z over Y plus Z. Okay, now this is close to additivity, and in fact, it is equivalent to additivity as we claim the bottom of the slide says, right? This property really is a rewriting of additivity. So in this context, it captures some notion of invariance of your decision with respect to addition of an independent random variable. Okay, let me now give you a second example, which now it's not about single agent decision problems, but multi-agent decision problems. It's almost a problem in social choice under risk. Let me give you a very pedestrian story once again. Imagine you have a bank, and this bank employs traders. And traders have to make choices between investments. Okay, so we have two trader 1 and 2, and trader 1 is an expert in pork futures, X, and has to choose between two futures, X and X prime. And by the way, the Chicago stock market actually, such futures exist. Now, trader 2 is working on something completely different. Maybe he's an investor in choosing between cryptocurrencies, or maybe an employee who has to choose the insurance contract, the insurance company to which insure the bank building. So he's making, again, a risky choice, but about sources of risk that are stochastically independent. Now, the CEO is not overseeing all possible combination of choices, simply writes a manual which specifies a function phi. So describes to each decision maker what sort of preferences over risks are in line with their expectations. And the manual says to choose A over B if this functional phi of A is greater than the phi of B. Okay, now the bank would like to avoid a situation where the following happens. We have these two decision makers who are choosing between independent random variables. Decision maker 1 chooses X over X prime. Decision maker 2 chooses Y over Y prime. But the final payoff that the bank obtains, X plus Y, is actually stochastically dominated by the payoff that is obtained if had the agents chosen the other options. Okay, so this is, think about this as some sort of desideratum about how this functional phi has to behave. Okay, and it can be shown, I will show in the paper, that phi, in order to satisfy this property, must be a monotone additive statistic. Okay, so it is the only type of preferences over risks that is robust to this sort of decentralization. The agents solve individual decision problems. These problems are independent, and we don't want the final outcome to lead to dominated choices. Okay, so given this claim now, right, comes the question, which is, okay, so what are exactly these monotone additive statistics? Any such statistic would be a solution to this problem. So what are exactly, what is this set of functionals? What do they look like? Any questions?
So I think you motivated additivity pretty well, but I still don't get why you need stochastically independence in additivity rather than just. So do you have some simple motivations of why you require additivity for stochastically independent random variables?
Well, one is that if you get rid of independence, not much is left, because then the only statistic will be the expectation. If you were to require additivity for all possible pairs of random variables, then you would be left with the expectation. But even in this context, right, maybe if the random variables trader 1 is choosing between are correlated with the random variables trader 2 is choosing between, then maybe there might be some motives for hedging, right? Maybe if the X is negatively correlated with Y, then maybe the bank may prefer. Then what I mean by this, if you right, so in this context, you definitely don't want that the resulting choices are stochastically dominated when the agents are solving correlated problems. But if you know that you're solving correlated problems, the very idea of specifying preferences for each decision maker is not very appealing. What we think is more natural is a situation like this, where the agents are solving independent problems, and maybe you wouldn't even expect that because they're solving independent problems, these property could ever, this combination of events could ever happen. I mean, initially our intuition was if they are solving independent problems, it must, for most functionals, for most statistics, it cannot be the case that the resulting choices are dominated. So, so what I mean is that this model, I think, makes sense exactly because these individual problems are stochastically independent, because this is where you would imagine that the centralization of choices to the agents would be harmless. I don't know if I explained that well.
Yeah, thank you.
Okay, there is another motivation that will come when we think about when we talk about time preferences.
Can I make a comment, because
Sure.
you just remind me of that. So even before you said, I'll show you when we get to time preferences how this thing is related. But both this example and the previous one, they really make me think more. So I'm gonna wait and see what you do with time preferences. But these, they really make me think of risk preferences, of course, because it's a risk environment, but in particular violation of independence. Like this example that you just showed is basically what in the behavioral economics literature people call narrow bracketing, right? When you have two different, and then you're basically saying we want this functional not to be subject to or susceptible to narrow bracketing. Like you don't want the
yes.
And then the previous example was also sort of a failure of the independence axiom. Well, if it was an additive, you would have had like a failure of independence, right? So you're saying that when I add the extra random arriving time, the Z one, my preference between the X path and the Y path shouldn't change, which has that independence feeling to me. So I'm just wondering, why, well, not wondering, I just wanted to make the observation that there are also puzzles, or interesting things to say in the risk preference domain. But I'm curious to see what you say for time preference.
No, thanks. So in this particular example, you could rephrase this as a model of exactly as you said. You could be rephrasing this claim and this little story in terms of narrow bracketing, right? So instead of having different decision makers while solving independent problems, you can imagine one agent who throughout the day or throughout the week is looking at different problems. Like, where do I go to fill up my car, and where do I go to choose for groceries, right? And maybe the price of gas and the quality of the groceries are independent random variables. And if you solve these individual problems separately through some preference over risk, then yeah, this property is saying that your preference over the individual problems should not result in dominated choices. And this is an old idea that is due to Rabin and Weizsäcker. So this is one connection with risk. We talk about it more in the paper, and if I have time, I'll come back to it. Okay, so
pardon?
Yeah.
Maybe last quick question on this slide. So is there any sense or any hope that if, for instance, I say instead of x and x prime being independent of y and y prime, maybe they are correlated in a certain way, would there then be any hope to transform the claim into has to be, a monotone supermodular or submodular statistic? So if I change independence into some sort of correlation, would I have any hope of translating that into, for instance, a supermodular or submodular claim on the statistic?
It's a good point. We haven't really looked at it. It's yeah, it is an interesting direction, but we haven't really looked at it at all.
Okay.
Okay. So what is the answer, right? What is the characterization? Let me first give you some example of monotone additive statistic. One I already told you is the expectation, which is monotone, and it is additive because it's really a linear function of the random variables. Some nonlinear examples are the maximum and the minimum of the support. These are bounded random variables, and think about the maximum of the support of it and the minimum of the support. Now, this is monotone, but it is also additive because the maximum of the support of the sum of two independent random variables is just the sum of the individual supports. Here is a more interesting example. What does this say? Imagine you have an agent with an exponential utility over money. Think about X really as an asset or a gamble. Then this is the certainty equivalent, this function SA, it's the certainty equivalent of this random variable for a decision maker with the absolute risk aversion coefficient equal to -A. Right, so we're looking at the expected utility, which is the expectation of this exponential function. Then we take the inverse. This returns us the amount of money that the decision maker finds as desirable as the risk X. This is monotone because exponential is an increasing function, but it's also additive, exactly because of the properties of the exponential. Additive for independent random variables. So as a function of the parameter A in statistics, this is also called the normalized cumulant generating function of X. And this function really defines a one-dimensional family of monotone additive statistic. And when we take the appropriate limits, this also subsumes the three examples at the beginning. This is the SA, right, in this displayed equation is only defined for A's non-zero, but when you take the limit of A to 0, you recover the expectation. When you take the limits of A at plus and minus infinity, you recover the maximum and the minimum of the support of X. Okay, so now the question is, okay, we have this one-dimensional family of monotone additive statistic, and is there anything else? It turns out that the answer is basically no. So if you have a monotone additive statistic, then it must be a convex combination or an integral of such monotone additive statistics. So we are looking at the certainty equivalent S computed with respect to the coefficient A, and then we're averaging over A. So if you think about this phi as a certainty equivalent of some preference over gambles, this is saying that this certainty equivalent is a mixture of certainty equivalents of Cara agents. So another way to put it is that the set of monotone additive statistics is convex. And these SA are the extreme points of the set of monotone additive statistics. Okay. So I want to give you a little bit of a proof sketch, because it turns out that it involves some ideas about some results about stochastic dominance and the effect of adding independent random variables that we think could be of interest also in other setups. So we have two properties, monotonicity and additivity. So the key first step, right, is to understand what byte they have when they are combined together. So we know they have byte, right, because of this representation, which basically tells you everything reduces to this one-dimensional family of statistics. So they must have some byte. So remember what monotonicity says. If X dominates Y, phi of X is greater than phi of Y. So here is a property that comes exactly because of monotonicity and additivity. Imagine you start from X and Y, two random variables, and then you add an independent Z so that X plus Z dominates Y plus Z. Okay. Now, if phi is monotone and additive, and this holds, this property of X, Y, and Z holds, then phi of X must be greater than phi of Y. Why? Well, because by monotonicity, phi of X plus Z has to be greater than phi of Y plus Z. And by additivity, Z cancels out, can be factored out. So if you have this premise that there exists a Z that makes X plus Z dominating Y plus Z, then you can conclude that phi of X is greater than phi of Y. This really is a content of monotonicity plus additivity. Now, the whole point, right, is whether this premise is vacuous. That is, what does it take for two random variables x and y to be such that you can find a third random variable z that is independent and makes them ranked in stochastic dominance. Now, if x and y are already ranked, then adding a third random variable that is independent will not change this. It's a simple computation, but intuitively makes sense, right? The question is this always the case, or are there more general conditions under which this can happen? For example, suppose x and y are not ranked. Can I find a z that makes the two resulting sums ranked? Okay, so one may intuitively think this is not possible, but it turns out it is possible. So here's the simplest example we could find, just also to mostly convince ourselves. So x is a gamble that pays 1 with probability 1/3 and 0 with probability 2/3. And y is uniformly distributed between minus 0.6 and 0.4. Okay, so x has higher expectation than y. The maximum of the support of x is 1, which is above the maximum of the support of y. The minimum of the support of x is 0, which again is above minus 0.6. So x is kind of to the right of y, but the two are not ranked in stochastic dominance, and that's because they just aren't. In the first picture here, there is the figure here, there is the two CDFs, and you see that they cross, so they are not ranked pointwise. Okay, so what happens when you add an independent random variable z? You are smoothing out these CDFs, right? Because you're adding noise. And it turns out that if z is sufficiently diffuse, you sort of disentangle this knot at 0, and then they become ranked pointwise. And for example, here, if you add a Bernoulli random variables that pays 0.2 or minus 0.2 with equal probability, then you obtain some two random variables, x plus z and y plus z, that are now ranked. Okay. So, okay, so these numbers, of course, were chosen carefully. So here is a general result that illustrates when this can happen. In an earlier paper, we studied the case where x, y, and z are potentially unbounded random variables. And it turns out that in that case, the answer of this question of when this phenomenon can happen is very different. And basically, whenever x and y are ranked in expectation, it's enough for them to be ranked in expectation, then you can always find a z such that x plus z dominates y plus z. The z usually has to be unbounded and with non-trivial dictates. So when you think about bounded random variables, then things change. And here's the result. Here's the key lemma in this proof. It says that if x and y are such that every certain equivalent SA, this SA, remember, is this one-dimensional statistic in the result, is certain Cara certainty equivalent. If every Cara certainty equivalent of x is above that of y, then you can find a z such that x plus z dominates y plus z. Okay, so another way to think about it is stochastic dominance is about all expected utility agents preferring x over y. Here we're looking at all Cara agents. And if all Cara agents prefer x over y, then you can find a z such that x plus z dominates y plus z. So how does the proof work? Is sort of a guess and verify proof. So if you take z to be a normal Gaussian random variable with sufficiently large variance, and then you truncate it to make it with bounded support, then this is going to work. And I'm not going to go over the argument, but the basic idea is that if you remember, right, in the PDF of normal distribution, there is an exponential term. And somehow that exponential term goes well with the premise that all Cara agents prefer X over Y. And in the paper, we have a proof sketch where we actually explain this a little better. So what do we get from this? Well, we get that if all Cara agents prefer X over Y, then any monotone additive statistic phi must assign higher value to X than to Y, exactly because there exists now this Z that makes them ranked. And so additivity, monotonicity, and additivity now have bite. Okay, from here, then some function analysis techniques will finish the proof.
Luciano, can I ask I want to ask a question that, first of all, if I'm wrong, you can tell me to check my intuition. And
okay.
then if instead I'm right, then, you know, it's another way to interpret this lemma. So can I rephrase in English this lemma as follows? If a Cara agent prefers lottery X to lottery Y, then I can always find an extra lottery or an extra source of noise such that the combined lottery X plus Z is preferred to combine lottery Y plus Z by every risk neutral agent.
No, it's both the premise and the conclusion are strong. The premise is here that X has to be preferred to Y by all Cara agents. All Cara agents.
All Cara agents. Okay, not a Cara agent, but okay.
And the conclusion is that X plus Z is preferred to Y plus Z by all expected utility agents.
Yeah, sorry, all expected utility. Yeah, sure. Yeah. Well, right, I was going. Yeah, you're right, of course. But I was going through reducing this taste for risk. So yeah, but every Cara agent has to prefer X to Y.
So this is just the premise is a stochastic order, the order defined by all Cara utility functions, and the conclusion is just what comes at the end of the lemma is a characterization of it, an implication of this order. Okay, so here's another way to approach this result. So here we're looking at the effect of adding independent noise to two random variables and then asking what are the conclusions in terms of stochastic dominance. There's another way in which we can aggregate random variables, which is to look at independent sums. So you can define another stochastic orders where we say that X dominates Y in large numbers if the sum of n independent copies of X dominates the sum of n independent copies of Y for all n large enough, right? So what happens when we take this sum with n large, right? This sum will put a lot of weight towards n times the expectation of X and n times the expectation of Y, but the tails of these sums, this distribution of the sum will also have large tails on increasingly large support. And this property says that this resulting distribution of n large will become rank in terms of stochastic dominance. Now, once again, you can imagine that unless X and Y were ranked to begin with, taking sums of independent copies of X and Y cannot create a ranking in stochastic dominance if they weren't already there. But once again, we were wrong in this intuition. And in fact, it was shown by Arbun and Nikita in 2008, a similar result to the one I showed you, that if, again, all Cara agents prefer X over Y, then X dominates Y also in this sense, in large numbers. So again, you can find n copies of X that dominates the sum of n copies of Y for all n large enough. So, and it is sort of interesting to notice that this work by Arbun and Nikita was motivated by things that are completely outside of decision theory. In fact, they were answering a question from the literature in quantum information theory. Don't ask me what it is because I wouldn't be able to tell you. Okay, so this is sort of the technical background behind this result. What do we do with it? Let me skip this. Let me skip this too. Let's come to risk preferences. So the first sort of application of this result is really to a problem that we could call a problem in social choice. So the idea is simple, right? I want to go back to this example of an organization, or it's like a bank or a company where there are multiple agents who are working on independent problems. So, and these choices are decentralized to them. So think about a large organization where we have many risky choices that involve risk that are being made, and they are not, these choices are not organized to a deliberate centralized process, but they are left to these people involved and with limited coordination among them. So for example, we may have one trader in a bank who is choosing between two assets, and maybe some other person who in the same organization who is choosing between two insurance policies. And what the organization cares about in the end is an aggregate of this random risk, of these sources of risk, right? Which simplest case is when the organization cares about the sum. So agent one may be choosing X1, agent two may be choosing X2, and what the bank cares about in the end is the sum X1 plus X2. Now, because these choices are about independent domains, the risk about the trader is considering is stochastically independent by the risk the person who has to choose insurance policies is considering. We may ask, is there much to lose when we do not coordinate these choices? And if we don't coordinate them, are the resulting choices of the organization compatible with basic tenets of rationality over risk, such as stochastic dominance? So let me give you the model. Let's say that we have two decision makers, A and B. And each such decision maker is endowed with a preference over gambles. This preference is complete, transitive, is continuous, and satisfies a basic notion of monotonicity, so that any random variable x is worse than x plus a positive constant. So the individual preferences at this point, you can see have basically no structure. We impose one axiom, which was first introduced by Rabin and Weizsäcker, of consistency between these individual preferences and what they imply for the organization. The axiom says, suppose you have two random variables x and x prime and other two independent random variables y and y prime. If agent A chooses x and agent B chooses y, then it's not the case that the resulting payoff x plus y, it's dominated by x prime plus y prime. Right? Dominating first order dominance. Okay, so we want to avoid the situation where the decentralization of the choices lead to a dominated outcome. And as Antonio said, another way to think about this model is a model of narrow bracketing or narrow framing. There is only one decision maker, but this decision maker applies different preferences to different problems that are stochastically independent, rather than applying one single preference over a joint problem, as a more textbook approach would compel. Okay, so what individual preferences are compatible with these ideas? Okay, with this property of Rabin-Weizsäcker? Well, two preference relations satisfy these axioms, in particular the Rabin-Weizsäcker axiom, even only if they are the same preference of a gamble, and they are represented by a monotone additive statistic. So in a way, this is saying that this axiom is perhaps stronger than it seems, and the only preferences that are compatible with it are preferences where the certainty equivalent of the individual decision makers are convex combination of chiral certainty equivalents. Right, and the relation with this paper of Rabin-Weizsäcker is that they identify the idea of Kara in the sense that they show that if the agents have expected utility preferences, then this axiom is equivalent to car. But they leave open the question of whether non-expected utility models can change this conclusion. And what we show here is a complete characterization of this class of preferences. That is, with the only preferences that are robust to this phenomenon are those that are complex combination of car certainty equivalents. Any questions, comments at this point? Okay.
I remember in the paper, indeed, as you said, they say that Cara is the only way to satisfy that property. But you're saying your result shows that even when you leave expected utility theory, you really cannot do much better than
Right.
a convex combination of Cara certainty equivalent.
Right.
Okay.
Okay. So let me now change topic completely and talk about risk time preferences for a moment. Let me go back to a very simple model that was introduced in the 80s by Fishburn-Rubinstein, which is the simplest model where you can talk about the trade-off between more desirable reward and a longer delay. So in this paper, they studied dated rewards, which are a combination of an amount of money that you get and the time at which you will get it. So think about this reward always as a positive amount of money or any desirable price. And what Fishburn and Rubinstein do is to study preferences over these dated rewards and study conditions about how these trade-offs are resolved by the decision maker. They consider 4 properties. And property 1, 2, and 4 are just basic properties. The first one says that the higher reward is always preferable, given for a fixed time. That earlier is always better for a fixed reward X, and a continuity property that is standard. The key idea that they study really is that of stationarity, which basically says the following: if you prefer a dated reward xt to another one ys, then adding a common delay d is not going to change your preferences. Okay, it's not going to change your preferences. And what they show is that this is really what characterizes the standard model of preferences over dated rewards, which is exponential discounting, right? So you have a utility function u over rewards, and you have discount factor r, and you discount exponentially the time at which you are going to receive your prize. So really like the typical functional form that we use in papers that have to do with the time and the discounting. So the way they motivate, the way now we understand stationarity in the literature is as a combination of the 2 ideas. The idea that the calendar time doesn't affect preferences and that the agent is dynamically consistent. So I'm not going to go into the details of this. There is a paper by Alevi that explained this very well, but the general idea is something like this. So imagine that your choice between 2 dated rewards can be made at time 0 or at time d. That is, I can choose today between these 2 dated rewards, but there can also be another situation where I have to make the same choice at that time d. Now, if calendar time doesn't affect my choices, then I should make the same choice both times. So this is saying that at time d, let's say at time d, I will choose xt over ys. Now, an idea that appeals to dynamic consistency is that I should anticipate today that at that time, I would make that choice. And now, if the choice then is not to be made tomorrow, but has to be made today, should be consistent with that too. Right? So if at time d, I will choose xt over ys, then at time 0 now, if I face the delay, I will have to make the same choice. That's sort of the two principles that are behind this axiom. So in the world of Fishburn-Rubinstein, the reward and the time are deterministic. There is no risk involved. But you can imagine easily situations where both the reward and the time are random. For example, maybe you make an investment and the payout of the investment is uncertain, both in the magnitude and the time at which the project is completed. You work on a paper together, you don't know exactly how good it is. You also don't know how long it will take you to finish it, and so on and so forth. So the dimension of risk about the reward, it's pretty well understood. There is much less work about risk over the time at which this reward is delivered, and that's where that's what we're gonna look at in this paper. So we're gonna look at time lotteries, which is a combination of an amount of money X, again, which is, for simplicity, I'm gonna take to be deterministic, and a random time T at which this money is delivered to the decision maker. And then we're just gonna try to see what exactly the Fishburn and Rubinstein standard axioms imply over this domain, or some natural extension of those axioms. So axiom 1 is that we're gonna keep the Fishburn and Rubinstein representation of the deterministic domain. And then we're gonna extend some of these axioms to the case of risk. So axiom 2 here says that earlier is better, also in a stochastic sense. A distribution of waiting time t that is stochastically smaller than s, it's strictly preferred by the decision maker. Continuity axiom 4 here takes the following form. It says that for every time lottery, there exists some deterministic time that makes you indifferent. So you can always reduce the random time to a deterministic time, some type of continuity. And then the key idea here is that of how to adapt stationarity to random times. And the way we adapt it is the following. We say, okay, if you prefer xt over xs, it's fine to keep the same amount x, not y, given the other axioms. If you prefer t over s, then the same ranking is not going to be affected, should not be affected by an independent common delay d. Okay, so the only difference between this condition and the standard stationarity condition is that d and t and s are random and d is independent. Oh, sorry. So why is independence here? Why does independence here make sense? If you try to go back to this idea of Halevi of stationarity is the combination of irrelevance of calendar time and dynamic consistency. There, the thought experiment is something like, suppose I make the choice now or I make it after the delay d, right? And then you appeal to some sort of consistency between these two situations. Here, what is the equivalent thought experiment? It's something like, consider making a choice now or at the realization of the delay d. And then again, you would like to appeal to some sort of consistency. But now the problem in general, when d is random, is that the realization of the delay d may give you information about the distribution of t in the distribution of s. Right? Maybe after the delay d is realized, I understand that now random capital T gives me a much earlier reward than capital S. But when instead D is stochastically independent, conditioning on its realization doesn't really change my preferences. Shouldn't really change my preferences because it's giving me no new information. In the paper, we explain this a little better and more in detail, but that's sort of the idea we appeal to. Okay, so
a quick question. So you already said it, but I missed it. So why do you have x and x versus x and y here?
Oh, we could have x and y, and it is just because we already keep the axioms from Fishburn-Rubinstein, and sorry, it turns out that given this 4, it's enough to look at the case where x and y are the same. Because once you have those 4 axioms, all you're left to understand is how do you reduce the random time to a deterministic time. That's what you're left with. And that's also what the representation theorem does. It tells you the following. So if you have a preference over this random time lotteries, then the axioms imply that it has to take this form. So again, it looks like a exponential discounting, but now t is random. So you can think about this representation as in 2 steps. First, you reduce the random time t to a deterministic time through a statistics phi, which is a map that tells you for which deterministic time you would be indifferent between the time lottery and the dated reward. And then once you reduce the risk to a constant, you apply standard exponential discounting. So it's not hard to show that these axioms I just wrote imply that this phi has to be a monotone additive statistic. And then from the representation theorem that I showed you in the beginning, we also know what this phi is. It's going to take this form, right? So the certainty equivalent of the random time t, again, the time that makes you indifferent between the time lottery and the dated reward, is an average of certainty equivalence of exponential discounting expected utility agents. So let me explain this better in the next slide, and also tell you why we may care about this. What does this say that is new on this topic? So let me first write down the whole representation, right? What is this saying? This is a representation of time lotteries. You have a utility function over money, then you apply discount factor R, and then you have this reduction of the random time capital T to a deterministic time. So what happens when you plug in a mu that is a Dirac measure at some coefficient, say minus R? Then you recover exponential discounting. So your V is the same as a standard model in 90%, 95% of papers where you evaluate a reward X at time T by taking the expectation. So this is a special case when mu is a Dirac. Now, one property of this standard representation, which is simple but not so often noticed, is that it implies that the decision maker is risk-loving over time. Here's a recent paper by Denarjet and co-authors exactly on this issue. So risk-seeking here means that you would always prefer a random time t over the deterministic time that is equal to the expectation of this. So it's really the opposite of what you think is natural under risk over money. That's an implication of discounting. Okay. There may be some dissatisfaction with this conclusion, and this recent paper and some previous papers also show that, in fact, the evidence about risk behavior over time is somewhat mixed. So some agents actually are risk-seeking over time, other agents are risk-loving, other agents go from one to the other. Okay, but this is one special case of this representation. What do you get if you change the measure mu? So if, for example, if mu is a Dirac at 0, then you get a representation that is risk neutral over time, right? You just reduce the random time to its expectation. If mu is a Dirac now at R, then you get this representation, which is now risk averse over time. Now the agent always prefers the expected time over the random time. When mu has some support over the positive and on the negative real numbers, then you get a decision maker who has a more nuanced attitude towards this type of risk. For some gamble may behave like a risk of seeking agent, for some other gambles may behave like a risk averse agent. So the takeaway here is that it is true that standard expected exponential discounting implied risk seeking, but there are many ways to extend exponential discounting to random times while maintaining stationarity. So if the focus is on stationarity rather than expected discounting, then risk seeking is not the only possible conclusion. And then from here, then one can ask more, right? We can ask, okay, then what happens if we risk also over the dimension X of the rewards? And then how does the representation trade-offs between the two different sources of risk, etc. But at least in this simple model, we think this can be an interesting point to think about, and a representation that has nests a number of possible attitudes.
Luciano, can I ask you a quick question?
Sure.
So I guess by what you said earlier, also another natural kind of special case or attitude towards time would be to look at ambiguity over time. And I guess in your case, this would be something like taking the limit to negative infinity of like this A coefficient that you call, or the mu itself.
Yeah,
Right?
You would it would be like an extreme type of pessimism, right? You would rank, you would only look at the maximum possible delay that you can encounter.
Yeah, I mean, I don't know if this is like interesting from like a behavioral theory perspective, if there's any work talking about like ambiguity over time, but I thought it seemed like an interesting case.
No, not that I know exactly, because even the papers that talk about risk over time, only the risk dimension is very small. So papers that maybe allow for subjective beliefs about the distribution of time, maybe there is something out there, but I don't know. I don't know of any such work. So it's really, even though I think it's a very basic question, there's very little work on it.
Thanks.
And yes, so it's exactly 7 p.m. and this is my last slide. So thank you very much.
Thank you. So I'm gonna stop recording now. And